Good morning. I would like to stay on the perception side and kind of continue the presentation from the previous speaker. So what I would like to shed some light on is to answer the question how automated vehicles can detect unknown objects that are unsafe, or how a complementary safety channel can ensure collision-free driving. But what I actually want to answer is the question what umbrellas, boxes, and harvesters have in common. Let's start with the boxes. So this is a typical ADAS application that you can see here. You see not that common situation. We have that wooden box on the road. You see the result. You see what the ADAS application sees. Actually, it sees nothing. It doesn't detect the box on the road. So what's the reason for that behavior of the system? The reason is how these systems are designed today. The typical design approach here is that the system, the neural network inside, at first needs to derive what type of object it is before it can derive where this object is located in the scene. So in other words, if it doesn't know what it is, it can't know where it is. So that's the issue with these systems. So we have this relation, first what and then where. Which also means that AI-based perception alone cannot ensure collision-free driving for automated vehicles. Let's have a look how these systems are built today. The typical approach is that there is a fleet of cars equipped with some sensors, and this fleet records some data. Then someone takes this data and annotates and labels the data. That draws all these rectangles around the cars, the bicycles, and the pedestrians. Once we have that labels, then a neural network is trained with these labels. And once we have the network, then the network is put in a car on the road. Let's assume we have a camera in the car, and now this camera observes the scene, and if there is a car in the scene, then this network will classify and detect this car, which is just another explanation or description of it does the what and where thing, right? And the same happens with the bicycles and also with the pedestrians, so there's no issue at all with that. But now the box is on the road. As the network hasn't been trained for the box, it is very likely that the network won't detect that box and the system fails. What we can do now is, ask the drivers to go back on the road and to collect, again, data of boxes. And when we have the boxes, then the developers, they train the networks again, put them in the car again, and then the system can finally detect the boxes. So problem solved. But then another object appears, which is unknown. This is a scene that we got from a customer. And indeed, this network of the customer was trained for motorcycles, but it wasn't aware that some of the drivers of the motorcycles are also wearing umbrellas. So the network was really confused by that and wasn't able to detect that. Which means there is, again, an object that the network can't detect. The important aspect in this slide are the little dots in the lower right area of the slide, which means that there will be always an object that is not known to the network. This is an infinite list that we cannot complete just by driving. Let's have a look at another perspective, or from another perspective, at the issue. If an automated car needs to or wants to drive autonomously, then it needs to plan a path. That's the path where the vehicle should drive within the next couple of seconds, 3 to 5 seconds. In order to plan this path, the vehicle needs to know where there is no object in the scene, where is free space. So that's the region where the vehicle can actually drive into safely. Which means the system needs to derive the free space. One approach for deriving this free space is taking the objects that are classified and detected by an AI-based or any system, and then it just defines that between the object, the detected object, and the sensor, it must be free. There can't be any object. That's the definition. And this is then simply done for all the objects that the system detects. We also have regions where there is no object at all. There the typical approach is that the maximum detection distance of the sensor is used, and again, by definition, we say, well, within that space, between the sensor and the maximum distance that the sensor can detect, there is no object if we haven't any detection of the object. And with that, the system then plans the path. In that case, very simple path. It's just a straight line because it seems to be free. Now, I guess you already see the issue here. Once the system does not detect an unknown object, which might be in that space, then it still assumes it's free space, and this is inherently unsafe. And this is also why I would like to declare this kind of free space, so free space that is derived from classified object. I would like to declare that a free space as unsafe free space. Another issue. If the automated vehicle needs to plan a path, it does not only need to know the free space at the current point in time, but it also needs to know the free space of the future, because it is the future where the vehicle wants to drive into. And in particular, if we have dynamic objects in the scene, this means that the free space itself needs to be predictable. And with that predicted free space, we can then plan a path. So now the question is, how can we make the free space predictable? For that, we need the information, the dynamic properties of the dynamic objects, which means we need the velocity and the driving direction, at least, from the dynamic objects. Let's have a look how this object dynamics is derived in the classical way. We see another example here on the road, and let's assume that the detector or the system detects the vehicle on the right side, and it gives a bounding box of that vehicle, 2D bounding box. At another point in time, it gives another bounding box. Then the system associates those two bounding boxes to each other, and then with some simple math, it can kind of calculate the velocity that derives from the shift of the bounding boxes. Now, again, I assume that you already got it. If the system is not able to detect the object, then of course it won't be able to derive the dynamics of the object. And if it doesn't know the dynamics of the object, then the free space that it needs for path planning gets outdated. And this is, again, an unsafe situation. There's one more issue that we see with these systems. Let's stay with the example of the harvester. The system may provide such a 2D bounding box of the harvester. And of course, there are more sophisticated algorithms that even provide 3D bounding boxes of the objects. Now, the system may now plan a path from these 3D bounding boxes. It's indicated by the magenta line here. You already see the issue again. The bounding box, in that case, covers only the part that is known to the system, because in that case, it wasn't trained for a harvester that accidentally has a tool on the front, which is partially inside the lane of the ego vehicle, of the host vehicle. So again, we have an unsafe situation. This time it's coming from the limitations of the bounding box approach that we often see in this AI-based method, and that is again leads to potential collisions. Now I'm at the end in telling you what doesn't work, and I'm ready to derive the requirements for safe perception. Such a safe perception needs to be able to deal with any object type, like the umbrella driver. It needs to be able to deal with any object shape, like the harvester tool. It has to be able to operate with static and dynamic objects that are in the scene. It should provide a consistent representation of the objects and the free space itself needs to be predictable. And of course, such a system needs to be able to support a bunch of sensor types. At least it needs to support a radar, LiDAR, and camera sensors. Now I would like to derive an alternative and additional or complementary perception from, let's say, the classical way. Again, on the left side, we have the classical way. There are all the objects. And from these objects, the unsafe free space is derived that we can't use for automated driving. To recap, that's the what first approach. So the system at first determines what type of object it is, and then it derives where this object is. And I would like to come to another approach that changes this, that inverts that direction, and at first derives where an object is, and then maybe later on takes care for what type of object that is. And this is what you can now see, or will see on the right side. So while on the left side, the system tries to answer the question, or tries to know where an object is, I would rather like to answer the question or know which space is occupied by an object. And for that, the world is discretized into these cells that you see on the right side. And for each of these cells, the system derives whether this cell is occupied by an object or whether this space represents, this cell represents free space. So for static objects, you can see on the right side, for instance, if a LiDAR or a radar hits such a cell, then we mark this cell as being occupied by an object. But we also want to know that this is a static object, because this will be important for predicting the free space later on. If there is a dynamic object in this scene, such an algorithm should mark those cells again as being occupied, but this time, additionally, the algorithm should mark these cells as being occupied by a dynamic object, and in addition, it should give an information where this object is going, so what is the velocity again, and what's the driving direction, because from that, we can later predict the free space. All the cells that are not hit by the sensor can then be marked as free space. Let's have a look how this looks with the Harvester example again. Let's put the grid first. Now you see that this is a grid that is closer to our production version of the grid. You can already see that we have multiple resolutions, so the cells have different sizes. That's very important for the runtime later on, for the computational requirements of the system. So let's start with the static object. On the left, we have this little reflector on the left side, which gets marked in red, indicating there is a static object. Then we have on the right side the harvester, and you can see how this algorithm supports the complex shape of the harvester and how the tool of the harvester is included in this representation. And in addition, to this information, we also get velocity and driving direction information for all the cells that are occupied by a dynamic object. Finally, we have the free space, which is predictable as we have all the dynamic information of the dynamic objects. And with this information, the system can now, again, plan the path. And if now the automated vehicle would plan a path like this, then now we can detect there would be a collision. And we can even say exactly where this collision would happen, exactly where the harvester tool is within this planned path that you can see with the red rectangle. Now I'd like to show you how such an algorithm can be integrated in a safety architecture. So this is a very simplified version of an architecture that is using AI-based perception exclusively or alone. You remember we have this unsafe situation because the output of the AI-based perception may not contain all the objects. So what we propose is to keep this or all the parts of this architecture and enhance it and complement it with a second channel. So you see on the upper side, you see the previous algorithms. You see the AI-based perception and the path planning. That's the same as before. And we would like to call this channel the performance channel, which performs the what first approach. In addition to that, you see in the second lane, we propose to add a complementary safety channel, which follows the where first approach, which is then diverse to the first channel, and which increases the probability that all the objects are detected in order to drive collision-free. So what the system does is now, again, the AI-based system detects all the objects, it plans a path, and then this path is not directly given to the driving function, but instead it's given to a collision check function, which uses the planned path from the upper channel, and the where first approach, the dynamic grid approach, to check this planned path for a collision, as we have seen it with the harvester example. And only if this collision check says, yes, this path does not contain any collision, then the planned path is given to the driving function. And if it detects a collision, then maybe some fallback path is followed to bring the vehicle into a safe state. Let's have a look how the dynamic grid looks in detail. So we have the same color coding here, which means that green means free space, red are all the static objects, and blue, later on you will see that, are all the dynamic objects. So now we are driving on a parking lot, so it's rather empty, and now we enter a public road, and we see the first dynamic objects, like this cyclist that is coming on the oncoming road. And we have another interesting situation here with a crossing van. We see how this object is properly determined as being a dynamic object, and also how the dynamic quantities are derived from that. Going fast forward, we see a stopped van, but concentrate on the vehicle that follows us. It's blue now. Now it's getting into a stop, changing its color from blue to red, so because now it's a static object. Now the vehicle goes again, and the vehicle behind us gets blue again, so the system again recognizes that this is a dynamic object. We'll soon enter a roundabout. Sorry. Before that, we see another small object, a pole on the left side. You also see how it's properly determined as being a static object. Now the roundabout comes. You can see how the dynamic objects in the roundabout are properly detected, and again, how all the dynamic quantities are properly derived. Now going back, the same route, and I have a last example for you there. you see a big object, a bus, and again, you can see how the system derives the dynamic quantities from this large object. During the last year, we, together with many customers and sensor vendors, evaluated the library with different use cases. We did it for cruising functionalities, we did it for L4 functions, L2 functions, for parking scenarios, for logistics automation. So we have many use cases where we have evaluations and interested customers using the technology. But we also evaluated how the algorithm performs using different sensors from different vendors, but also how it performs with different sensor modalities. So with imaging radars, LiDARs, but also with monocameras or even stereo cameras. All these were evaluated. If you want to know more about this, please also visit our booth. We have some more details on that there. Last but not least, there are also some non-functional benefits of this algorithm. As it is based on statistical methods, it does not require additional training data. So this is clearly an advantage compared to other methods. From a compute performance perspective, this algorithm runs on ARM CPUs, which means it does not require any additional GPU or any other sophisticated execution hardware, and we developed this according to the ISO 26262 for systems rated up to ASIL B. Thank you for your attention, and now I'm happy to get all your questions.
Thank you, Eric, for the informative presentation and for the complete storyline. So I'm sure you have some questions for Eric. Here we have one.
Thank you for the interesting talk. And first of all, a thumbs up specifically that you considered also the functional safety aspect, because most talks here are just about the performance, everything. Of course, functional safety, you said it's ASIL B compliant, is also very important. But at the same time, I'm a functional safety guy. It raises the question to me why it is only ASIL B. This would mean, of course, you can do an ASIL decomposition. The main part is ASIL B of D. I assume that hitting a VRU is ASIL D at high speed. And your additional channel also ASIL B of D. So it sounds reasonable at first. But earlier in your talk, you explained that the primary channel, the performance channel, has inherent safety gaps. So I think it's questionable to do an ASIL decomposition, which means your safety channel would need to have a higher ASIL. So can you explain why you think ASIL B is an appropriate level here?
Thank you for the question. I would consider that as highly relevant. But I would like to split that. I would like to split the functional safety aspects and the SOTIF aspects here. And the approach that I presented is some sort of a mixture, and it somehow addresses both aspects. On the one side, as you said, we could do an ASIL D decomposition using 2 times ASIL B from D. That's one part of the story. But I would like to split that, and I would like to split the SOTIF part and would not, let's say, mix that with the functional safety part here too much and say, well, the other motivation of doing the second channel is the performance issue of the first channel. So it clearly answers the SOTIF question of the first channel. So that's, let's say, the functional answer. On the other hand, we also get the requests from the customers that ask us to provide an ASIL B component that they can plug into their system, which they derive from their safety analysis. So of course, it's also a business question, and it's also a question: what does it cost to produce such a component? But at the end, it's always or what we propose is to have a look on these both aspects, so SOTIF and functional safety, and to discuss those two questions together, and then find a solution where both aspects are addressed. I know that this question can always be questioned whether this is the right approach or not. But what we propose is to discuss this together, functional safety plus SOTIF.
Thank you.
Right, any other questions? Here we get one.
Hi. I would like to know more about the logic of the dynamic grid, especially in the case when we use, for example, radar, which a lot of false positive and LiDAR. So what is the logic behind of dynamic grid if in one cell we have one object detected by one sensor and not by another one?
Yeah. So there's no clear answer to that question, unfortunately. This heavily depends on the use case that you have in mind. We have customers that use this system with one sensor modality exclusively, like only with LiDAR. We have customers that use it only with radar, but we also have customers that want to combine that in terms of a sensor fusion. But again, there is no answer to that, because you can configure the system and you can tell the system how it should behave when two sensors provide, let's say, information that doesn't fit together or that conflicts each other. So from our perspective, as a provider of a library, we don't define this behavior, but we offer the possibility to configure the behavior depending on the use case that you have in mind.
We have time for one more question.
Hi. Just a question, because it was really nice to see this optimization of perception and drivable path and all that. And I understand if you have detection from your sensors, then you have a best way to perceive it. And I'm thinking about snow. And if you have snow and say that the sensors can detect it and it's giving you that information, it's still an undrivable, unsafe zone for you. Whereas as a human driver, I would drive in the tracks that I see in the snow. How do you address that?
Yeah. So, of course, this solution. Or thank you for the example with the snow. And indeed, if we talk about, let's say, level 5 application, then we need to be able to deal with snow and to drive in snow. I don't know whether this approach addresses this issue. But what I know is that with that approach, we can today address L4 use cases with limited ODDs. For instance, doing automated driving without a driver in fenced areas, like intra-hub logistics automation use cases. And if we have that amount of snow in that area, then this just kind of limits the availability of the system, but maybe the overall business case of that use case is still fulfilled. But you're right, in the future we also need to think about snow.
All right, thank you very much for your active participation. Thank you, Eric, for your detailed answers. Let's give Eric a round of applause. Thank you.